Fully autonomous self-driving vehicles are one of modern science's greatest goals. An endless number of attempts are currently in progress to reach that goal. The Dreams for Cars approach employs a multi-layered system of simultaneously operating directives that all have access to real-time vehicle sensor data. Because the vehicle and its environment are constantly changing, so each directive changes what it allows and what it prohibits the driving agent to do, which is why these directives are most commonly referred to as affordances. These continuously varying affordances then compete together to be activated by the self-driving agent at any one moment. This one action choice of the driving agent is called the emerging behaviour. Since this occurs in real time, this process of producing emergent behaviour or action is very rapid and adaptive. The technical term for this multi-layered system is subsumption architecture, where higher levels are able to integrate and combine or subsume lower levels. Examples of lower base directive layers are avoid collision, a restriction directive, and exploit affordable space, a proposition directive. Examples of higher levels are lane follow or lane change left. This interface represents the multiple directives or affordances acting on the vehicle in real time. This is the bird's eye view, which represents the vehicle, the legal corridor, which is the portion of the road the car is legally allowed to use, and other objects such as the oncoming vehicle and the pedestrian. On the top right, there is the corresponding camera view showing the whole road. In this example, the legal corridor is the rightmost lane, and the same objects present in the bird's eye view are present here. A panel representing the self-driving agent's longitudinal intention and state is shown top middle. It shows 4 alternative conditions. Free flow, if the vehicle longitudinal control is not limited by objects' legal speed limits or curves. Car following, when the longitudinal control is constrained by the need to comply with an obstacle ahead, not necessarily a car. Speed limit, when the speed must be adapted to the next legal limit. And curve, when the speed must be reduced for a next curve. The current state is highlighted. At the bottom left, there is a panel representing the lateral state and intention. The panel shows 3 distinct affordances or possible options: remaining on the current legal corridor, or moving to an adjacent corridor left or right. In the example, there are no legal affordable corridors on both sides, hence the squares are grey. If there are multiple affordances, the chosen affordance is highlighted, in this case staying in lane, and the others are dimmed. For every affordable lateral corridor, there are 2 sub-panels. The bottom one shows a 3D representation of the salience map. The top one is an intermediate step in the computation of the lateral salience, which is related to the estimated probability of time to lane crossing, given a particular lateral control choice. On the right, there are 2 final panes. In the middle, the lateral salience, which visualizes the range of lateral control for remaining in the corridor. This is the lateral cross-section of the 3D salience map. At the bottom, a chart shows the inhibitions. Absolute inhibitions are in red and partial in yellow, and they are produced by the obstacles shown in the bird's eye and camera views. The inhibited regions indicate the combination of lateral and longitudinal control at risk of collision. The lateral salience map and the inhibition map are related to the selected directive or affordance highlighted in the lateral state pane. The green-white boundary on the inhibition map visualizes the position of the maximum longitudinal salience. A control selection within the green area means the car complies with the speed limit. White means not to comply, but there is no collision. A tiny blue circle indicates the instantaneous longitudinal and lateral control choice selected by the agent. This choice, propagated backward in the lateral and longitudinal state panels, identifies which directive or loop in the multi-layer system or subsumption architecture corresponds to the chosen control, i.e. the agent's longitudinal and lateral intentions. The reactivation of the subsumed loops permits us to reconstruct the emerging behaviour in every detail. An interesting notion related to the inhibition chart is the notion of awareness. Even if the agent chooses the action indicated by the blue circle, the inhibitions corresponding to the obstacles make it aware of them. Even if the agent does not need to choose actions in the red regions, it knows that the actions are prohibited. Here, two vehicles not shown yet in the camera view are going to collide on the motorway with the self-driving vehicle. They produce inhibitions that approach the action chosen by the agent. The inhibitions of the obstacles overlap the range of lateral control that permits the vehicle to remain in the lane. So the only option for the agent to stay in the lane is choosing a longitudinal control towards the bottom of the chart, which means decelerating. The selected action is also shown in the 3D salience chart. The chosen longitudinal control is at the bottom edge of the partial inhibition, which automatically produces an emergent car-following behaviour. As the gap opens, the self-driving vehicle resumes speed by approaching the speed limit and merges with the motorway. Notice that when the agent enters the motorway, a left lane becomes available and the corresponding but not selected, i.e. dimmed affordance, appears. After completing the approach phase, the self-driving vehicle enters the car-following state. Note that the selected agent touches the obstacle inhibition and it would not be possible to travel any faster. The two vehicles ahead proceed with the same speed and there is no added value in moving to the left lane. The changed left affordance exists, but it is not selected. Note the dimmed colours. Because changing lane would result in the same limit for longitudinal control and therefore there is no gain. Now the obstacle on the left accelerates. Immediately its inhibition in the control space moves upward and the change left affordance wins. The winner peak is shown in the lateral state panes because switching to the left lane is faster. Hence the agent intentionally switches to the left lane while the longitudinal state remains car following because it is following the left car. When the lane change is completed, the agent has two options: remaining in the left lane or returning to the right. The latter wins because lanes to the right are slightly biased to favour the legal recommendation to return to the right when possible. The winner peak in the lateral intention pane corresponds to a path that will re-enter the right lane after clearing the obstacle to the right. Note that the intention of returning to the right after completing the overtake is taken very early, well before the right obstacle is cleared. A vehicle arriving from the rear in the fast left lane is first detected and it blocks the lane change option. Note that only the trajectories that do not complete the lane switch survive on the salience map on the left pane. Now the fast vehicle frees the left lane. The salience map for left lane change widens, including complete lane change maneuvers. However, the agent does not move leftwards since the current lane it is in is free. The obstacle decelerates and cuts in front of the self-driving car. The winner action is now the left lane change. As soon as the predicted obstacle path indicates the cut-in, the agent plans to overtake. The overtake maneuver ends with a return to the right lane. Unusual or corner cases may arise from incorrect and unwise behaviour from other road users. Here, the self-driving vehicle stops because of the inhibition produced by the red traffic light. Crossing vehicles produce an additional inhibition to the same road region in front of the self-driving car. When the traffic light turns green and the crossing vehicles stop, the road in front of the self-driving car would become free, permitting the vehicle to start. However, the simultaneous movement of the pedestrian keeps that region prohibited, and the self-driving vehicle does not begin to start regardless of the green traffic light. Here is another example of a possible corner case. The crossing traffic does not give way. A safe stop manoeuvre emerges from the inhibition caused by the crossing vehicles. This situation combines a few unusual elements. The lane is 25 meters wide. There is a stationary vehicle far ahead in the lane, and there is an abundance of room to pass on either side. Two vehicles follow the self-driving vehicle closely on both sides, at slightly different distances. A traditional self-driving system that we tested would stop the car behind the stationary vehicle because it is a busy lane and it wouldn't consider the unusual width of the lane. Such behaviour is dangerous because other drivers around would not expect that kind of behaviour. Common sense would suggest letting the nearest rear car on the left pass and then moving on the left to pass the stopped obstacle on the left. And that's the emerging behaviour of the self-driving car. Here, the stopped vehicle ahead is detected. The self-driving vehicle then finds two classes of actions and considers the faster one, corresponding to passing in front of the right car and to the right of the obstacle. However, the car on the right gets closer and closer, and this possibility soon vanishes. The only remaining affordable action is tailing and stopping behind the far obstacle, as the two cars on the sides do not allow lateral movement. Finally, the action of following the car to the left emerges and is chosen.